Okay, so good evening, and let us get going for today's colloquium. As you see, today's colloquium is a kind of part two of what on the development of SiPM based imaging camera for 4-meter class telescopes. As you recall, the part one was given last week by Shobha Kerao. She is here. And so this is going to be the part two, the continuation of this particular work. So Sandeep, of course, is very well known to all of us, especially those who work on the instrumentation, electronics in particular, from not only from the Department of High Energy Physics, but I think all of the institute. I think it is also a good time for me to kind of say this, which is of course not specific only to the group that I'm about to mention, but also I think true for many other groups. Namely, there is a lot of instrumentation work that these groups do, which have far more applications and readily usable kind of modules by many other groups as well, both within the institute as well outside the institute, who are engaged in similar activities, namely high energy physics, astrophysics, and nuclear physics, and so on. The particular group, maybe I should say the previous experiment on which many of the same team was working, has developed a large number of the NIM-based, CAMAC-based, VME-based, and also standalone modules, which have found extensive applications elsewhere. And you will agree at the end of today's talk, then, there's similar kind of efforts which are on the backbone of all these high-energy nuclear and astrophysics experiments, which you will find, I'm sure, not just the concepts, but actual modules and systems could also be more or less readily used. And the second point you will also notice is that, many of these or all of these efforts are also almost indigenous. I mean, in the sense, the entire thing, whether it is electronic design, mechanical design, ergonomics, thermal considerations, integration, packaging, cabling, you name anything, and the whole thing is actually calibrations and so on. All of them have been originated within the group, and except maybe for want of integrated circuits or components, rest of it is actually done indigenously. You'll actually see that happening. So I think I thought I want to share this, and it is a nice opportunity to share this just before Sandeep's talk. So I thought I will share this. And so second thing, I really want to make an appeal. It's not connected with Sandeep's talk, but I want to make an appeal that it often happens because, to the colloquia, once the main talk is over, due to various reasons, we get up and go away. And so I want to appeal to all of you to also wait till the question answer. Sometimes question answers and discussion could be equally interesting, number one. And second thing is, even if you have to really rush out, I request sincerely to at least have a cup of coffee, tea, what was made available. Sometimes we order 70, 80 coffees and we only see only 50 or 30 consumed. So this is an appeal. Please don't take it otherwise. But I think we all must try to kind of follow this. Thank you very much for listening to this. Coming back to Sandeep. Sandeep did his MSc in electronic science from Kurukshetra University way back in 2003. And he joined TIFR, this particular group, way back in 2005. He's quite a veteran, almost 20 years into the institute, specializing in the electronics and instrumentation. Of late, he works mostly on the FPGA-based and VLSI-based devices, and very complicated electronics. Some of it is going to show to you. Incidentally, he also just submitted his PhD thesis to Punjab University, and he's in field of research is electronic instrumentation for high energy physics experiments. And of course, Sandeep has been actively involved in the HAGRO, which is at Pachmari, and which is now closed. And later on, they also had series of other activities at Hanle. It is called Hagar. And of course, as the name says, the title says, this particular thing is meant for a 4-meter class telescope, which is right now, I understand, is in Mount Abu. And it's likely that this equipment will also be shifted to Hanle. So that is their plan. But today we are going to hear more about the instrumentation work from Sandeep. Sandeep, over to you.
Thank you, Dr. Satyanarayan. So today I will talk about this part 2 of development of SiPM based imaging camera for the 4-meter class telescope. These are the outline of my talk. First, I will give a short introduction about this very high energy gamma ray observation. And then I'll move to this camera, which we have developed with specifications, and then followed by this data acquisition chain for 1 pixel and complete backend electronics. I'll cover trigger scheme, software scheme, and then few test results. So Earth's atmosphere is not transparent to radiations from ultraviolet and higher energies because of their interaction with the atmospheric nuclei. So to observe them, one has to use these satellite-based detectors, or if observation is to be done from ground-based, then it has to depend upon this secondary particles which are generated due to their interaction with the atmospheric nuclei. When a gamma ray enters the Earth atmosphere, it gets converted into PDF.
Control L.
When a gamma ray enters the Earth atmosphere, it gets converted into electrons and positrons, which further interact with the atmospheric nuclei and generate the secondary gamma rays and a cascade of charged particles. When these charged particles pass through this atmosphere, they generate the Cherenkov radiations by Cherenkov effect. So these Cherenkov radiations reach to the Earth in the form of a cone of about 250 meter diameter, and imaging atmospheric Cherenkov technique is the most developed and widely accepted technique for the ground-based detection of very high energy gamma rays. So in imaging atmospheric Cherenkov technique, we in imaging atmospheric Cherenkov technique, a large telescope is used for taking the longitudinal profile of the shower generated in the atmosphere. So for this, when these cosmic ray particles, they enter the Earth atmosphere, they also generate the similar type of Cherenkov showers, but the profile generated by them is more irregular, whereas that generated by this gamma rays, it is quite regular and elliptical in shape. So on the telescope, there is a this is the telescope, this type of telescope, where a large collection area, and at the focal point there is a camera which will capture the Cherenkov shower image. So then by using sophisticated image analysis algorithms, so it is analyzed whether that particular image is produced due to that cosmic rays or the gamma ray shower image. So this is the Cherenkov light and NSB spectrum, which is produced by this interaction. This wavelength varies from 300 to 700 nanometer and peak at about 350 nanometer. So this light reaches to the Earth in the form of light flashes, and it is not continuous. So number of this light is very faint, and number of photons per pulse is about 100 photons per meter square at 1 TeV energy. So because this is a faint light, so all these observations take place during clear and moonless nights. And duration of this pulse is about 3 to 5 nanoseconds. So an ultra-fast sensor is needed to record all these Cherenkov light shower images. So there are few detection challenges as this is faint. So that's why observations are done in the moonless and clear nights. So this restricts the duty cycle of operation of these telescopes to 10%. That is about 1,000 hours in a year. And huge night sky background, because this telescope will operate in an outdoor environment where this light from the night sky background will also be falling. So rejection of that also is a challenge. And Cherenkov light flashes which are generated by these cosmic ray images, those also have to be, those also pose a challenge to the detection of gamma rays.
Why the picture is very spherical instead of spherical? The gamma ray footprint is elliptical.
Gamma ray footprint is elliptical. So when this, as I told in previous slide, when gamma ray enters the atmosphere, so only these two type of charged particles, electrons and positrons, are produced. They further interact, and so basically this fixed type of processes are involved here: pair production, then Bremsstrahlung, and this Cherenkov effect. So which is by which this one. Whereas in case of cosmic rays, this different type of particles are involved and different type of processes are involved. So that's why the image produced is more irregular. And
but shouldn't it be a circular?
Sorry?
Shouldn't it be a circular kind of thing? If you see the cross section.
Yeah, that circular, okay, that this is longitudinal profile we are seeing. So it appears like this elliptical. Whereas other particles like muons, etc., they produce again that different image. So image shape will tell about the particular particle type, and the total photon content in the shower will give an estimation of the source energy. Okay, so because of this small duration of this Cherenkov flashes, so an ultra-fast sensor is needed. Conventionally, these photomultiplier tubes were used at the focal plane of these cameras for detection of these light flashes. But with recent advancements in semiconductor technology, so silicon photomultipliers have come as a viable alternative to these photomultiplier tubes. So our group has developed a camera for detection of these Cherenkov light flashes, and the camera will be having 256 pixels, field of view 5 degree by 5 degree, and in place of photomultiplier tubes, we are using silicon photomultiplier as a pixel light sensor. And because silicon photomultipliers, they are immune to that light, so they can be operated in partial moonlit conditions. Thus, it will help in increase the observation duty cycle of the telescope. And hollow light concentrators are used at the pixel sensor front, basically to increase the basically to avoid the requirement of using a large sensor and avoiding the night sky, the stray light coming from the nearby objects. So pixel dynamic range is 1500 photoelectrons per pixel with single photoelectron resolution, and we will be recording pulse profile at 1 gigasamples per second sampling rate. And we will be having a user selectable trigger scheme, 3 or 4 non-collinear nearest neighbor pixel. Expected trigger rate is less than 100 Hertz, and physical size will be about this much. Weight should be less than 100 kg because the camera has to be mounted at the focal plane of the telescope. So weight limitations are also there, and power consumption should be less than within 500 watt. So to avoid the stringent cooling requirement by the camera electronics. Eventually, the camera will be tested at one of the vertex element of the tactic telescope array at Mount Abu. And finally, after a satisfactory performance test, the camera will be moved to the Hagar site at Henley, Leh Ladakh. So in like other cameras, so first part of the camera is the photon detection plane. So 256 pixels of the camera, they are divided into 16 clusters, with each cluster will be having the 16 photomultipliers. So this is the silicon photomultiplier which we will be using. This is a 13 mm by 13 mm array with 16 subpixels. We can see 4 by 4 array, and in each subpixel there is 3584 microcells of 50 micrometer pitch, which we call that micropixels. And this is the light concentrator which will be mounted at the front of this camera pixel. These are few of the specifications of this sensor. So this is the simplified data flow diagram for single pixel. Here, this is a silicon photomultiplier mounted on the sensor mount board, and to save the cost, power, as well as space. So these subpixel pairs are passively shorted, and so 8 analog signals, they are coming to the pre-amplifier board, where they are pre-amplified, where they are amplified, shaped, and then summed to generate a pixel signal. This pixel signal again passes through 2 chains, low gain and high gain, to cover a wide dynamic range of 1500 photoelectrons, as well as maintaining a good signal to noise ratio at the single photoelectron level. And then we are using this analog sampler to sample these signals. And then once a trigger occurs, so this stored sample, they are digitized by the ADC, and then they are stored through this chain to the storage media. Then one of this high gain version, this is used for measurement of night sky background. And for this, it is applied to that comparator, where we can here we can set this NSB threshold, and it finally the output goes to the scaler. Another this copy of high gain version, it is used to generate the pixel triggers. So this again further this information will be laced, and then this information also goes to the camera trigger system, where the final trigger signal will be generated. And there is latch also. So with latch information, this will be used for validating the event signal. So
have sort of AC coupling at almost 3 stages in the signal.
yeah, yes.
Want to say something about it? I mean, did you actually notice that there are large offsets coming in, or what was the reason?
Okay.
To avoid as much as possible.
Yeah. Okay. So this first stage coupling is not there. I forgot to remove this one. Coupling is at this stage. AC coupling is removed. So basic thing, if some offset is coming, so that will reduce our dynamic range. So for that purpose we use. So here this low gain and high gain amplification is done in 2 stages. So between these 2 stages, okay, we employ this coupling, AC coupling.
But you also have right up ganging up.
That is ours is the transimpedance stage is a discrete component. We are using the transistor-based circuit. So if you don't use the AC coupling, the biasing of the transistor. So that's why you have to use it.
How do you separate the low gain from high gain?
How do you
Separate the low gain and high gain. How do you distinguish between them?
Okay, so low gain and high gain versions, okay, they are not separated. This single signal only, okay, it is passed through two paths. Basically, to accurately digitize the small signals with good signal to noise ratio. Otherwise, we have to use a ADC with which is having that large number of bits. So
I
to
mean, what is
avoid
your
using
criteria to define a signal as low gain?
any signal,
What is your criteria to identify a signal as a low gain and then other is?
no,
Or
it
you-
is the one signal, one that pixel output only. So here we keep gain less than 1 so that it can cover the full dynamic range of up to 1500 photoelectrons. At the same time, we want that this small signals, they should be accurately digitized. So that time we use the SiGain version for if large number of photons are falling on the camera, then this pulse, it will be saturated and we will be using the low gain pulse as we are recording the pulse profile. So for low, when less number of photons are falling, so that time we will be using this pulse profile.
So low gain is for high amplitude signals.
Yeah, I think
Yeah.
I understand your question. So Sandeep, essentially what you have to say is, you're not making any distinction. You are going to record both the data.
Both the,
You pick up the one that is closest to the saturation
yes,
or whatever, that means you had the maximum gain. Is the data that you take.
Yeah.
The saturation happens from the digitizer. So you have to digitize 1500 photoelectron information within the range given by the whatever digitizer. So that's why we keep the other one is just to find out the gain for gain calibration. You need something above your noise level. So that's why we amplify it maybe some 20 or 30 times so that we can see the pulse clearly. But we need to cover the dynamic range.
Yeah.
In high gain, what happens is saturate much early, maybe 100 photoelectrons.
Those we can see by look. Yes. So that's-
Yeah,
Yes.
yeah.
Yes.
so this is full camera data flow diagram. So here are the sensor mount boards. On each sensor mount board, 16 pixel sensors, they are mounted, and so 16 such these things are there. Then their output is coming to this preamplifier board. 64 such boards are there. One preamplifier board will serve to the 4 pixels. Then this 64 into 4, this many signals, they are coming to the digitizer system where we are digitizing those signals after receiving a final trigger system from a final trigger signal from another control and trigger module. So then the digitized data is transferred to data concentrator module and then finally to the PCs. And here is the bias system for all these silicon photomultiplier mount boards. And this is works under control from the Raspberry Pi and finally from the PC in the control room. So 4 PCs are used, one for data concentrator, another main console which controls overall operation of the camera and monitors some of the parameters. This is database PC which keeps the database record of all the pixel sensor calibration constants, etc. And this is bias console PC which displays the monitoring status of this bias supply. So this is pictorial view of the camera. So this electronics mode, this sensor mount board is here at this one, and in front of this light concentrators are mounted, and just behind that this preamplifier cards are there, and this bias system is there. So these are housed into an assembly that we call pixel cluster module. And then these preamplified signals are taken to the backend crate for final digitization. So keeping the same modularity, again, these 16 digitizer modules are there. Each one will serve to the 16 pixels, and there is a one data concentrator module and one control and trigger module. So as already, okay, this is covered. There is, although there is no definite line between this dividing data acquisition system in front-end electronics and back-end electronics, but for our camera, this preamplifiers and bias card up to this part we are considering as front-end electronics, and remaining digitizer and data transfer system trigger generation, that is part of back-end electronics. So this part was covered in the part 1 of this talk, and now I'll focus on the back-end electronics only. So this is the camera front end. Here you can see pixel cluster module. This is sensor mount board. SiPMs are mounted. This is with all SiPMs. So, and this is a bias supply board. It caters bias to 8 SiPMs. So 2 such cards are there. There is another low DC voltage supply board which supplies DC voltage to all these electronics in the front end. This is light concentrator assembly which is mounted at the front of this sensor mount board. So now coming to the backend electronics, those low gain and this analog outputs from the preamplifier, they come to this cluster digitizer module where low gain and high gain version of this is generated, and then this is applied to another card, DRS based digitizer board, where this signal conditioning as well as there's some analog storage of the signals is done by using this DRS4 chip, and then finally it is digitized by using a 14-bit ADC, and an FPGA is used on this board for overall control and managing the digitization operations. So 4 such this DRS-based digitizer boards are there in a cluster digitizer module, and on the motherboard there is a FPGA where we record this latch information and this various trigger rates and trigger logic for this cluster of 16 pixels is implemented. And this such 16 modules, they are connected to this common data concentrator module and control and trigger module via the backplane. So now I'll come to this camera trigger system. So main aim of the trigger system is to distinguish between interesting air shower Cherenkov events and the noisy events generated due to the night sky background light. So main difference between these two types of events is that Cherenkov showers reach to the camera in a correlated time and in a compact space, whereas night sky background photon reaching to the camera, they are randomly. So our aim is to distinguish between these two types of events. So to achieve this, camera trigger system is structured in 3 levels. At level 1, individual pixel triggers are generated, and at level 2, these trigger signals are generated for the cluster of 16 pixels. At level 3, final trigger signal for the entire camera is generated. So what are these level 1 and level 2 trigger signals? Any high gain pulse crossing a set threshold generates the level 1 trigger signal. And level 2 trigger signal, 2 types of triggers are there. One is that full trigger signal, a combination of 3 or 4 non-collinear nearest neighbors of a pixel in a cluster crossing the set threshold in a given time window of about 10 nanoseconds is assumed that camera has detected a Cherenkov event. So like here I have shown for one of the cluster of 16 pixels. So here 16 pixels are there, and if 4 of these, they are seeing this Cherenkov light at in a given time window, then we assume that this is a Cherenkov event. And like this 9 combinations are there in a this pixel cluster module. So now, because all these pixel cluster modules, they are adjacent to each other, so there may be some cases where some of the pixels are on the boundaries. So here partial 1-fold triggers are generated, this at the corners, and similarly this partial 2-fold, where these duplets of the pixels, they are considered for generating the full trigger signal. So all these partial trigger signals, they are resolved in the control and trigger module of the camera. So this is the level trigger scheme, level 3 trigger scheme. So any full trigger which was generated at level 2, that itself can act as a final trigger system, whereas these partial triggers, means boundary triggers like 2 duplets from one PCM and 2 duplets from the nearby PCM, so they can also form a full trigger. And similarly, like case of 1 pixel from the 4 PCMs, this can also form a full trigger signal. So all these boundary triggers, they are resolved to generate the final trigger. So now in case of this cluster digitizer module, we are sending this single signal only. So whenever a partial twofold is generated, so a pulse goes to the control and trigger module. So along with this pulse, we also send the trigger hit pattern, because we have to know that whether those duplet is from this side or this side, which duplet participated in this event formation. So trigger hit pattern of all 256 pixels from the respective CDMs is sent to CTM, and it generates the event validation signal, and which initiates the data collection process. So, yes. Yes.
So I'm going to also describe a little bit about how you arrived at the particular threshold, because the SiPM also may have some amount of background noise, and how you discriminate and how will it affect the threshold to affect your final data. I'm going to talk about right now we can figure the threshold.
Yes. So that is arrived, yeah, in the result section, I'll show that how this trigger threshold is decided. So that time I'll cover. So from the lab test and the first some engineering test runs or physics runs, they will be taken at the camera site. So from there, that pixel rate versus trigger threshold curve will be taken, and based on that, we decide that where to keep the threshold for a particular pixel. And usually in this type of cameras, this 3 or 4 non-collinear nearest neighbors. So usually this factor is this value is taken from 2 to 5. So if we take a very small number, then this chance coincidence rate will increase, because there may be chances this NSB which is arriving to the camera randomly, that may coincide with one of the Cherenkov event, and it may trigger this one. So, and keeping a high value of like 5, 6 or 7, so that will chance coincidence rate will be low, but we may miss some the genuine triggers with that.
Are you saying that these both the combinations as well as the threshold, etc., will fine tune at the site?
Yeah, these will be fine tuned at the site.
So you have all of these.
Yes, all this hardware is designed with quite configurable hardware is there. Yeah, user can decide. So earlier we had worked with this FPGA development boards bought from the vendors. So, but for this camera development, we had to develop the real hardware. So to get some confidence, first we selected a FPGA which can which could meet our all these module requirements, and then we first developed a general purpose FPGA development board to test some of the features. So this is the board which we developed. We selected a Max10 FPGA from Altera. So it is a 144 pin that IC with 40,000 logic elements. And on this board, one Gbps Ethernet module was also used to provide Ethernet connectivity. So one thing compared to other FPGAs in this series of FPGAs is that for storing this configuration, firmware configuration, so external flash memory has to be used in other FPGAs, but this FPGA has internal flash memory where we can store this firmware configuration. So we started from this board, and then next, after getting confidence, we developed this DRS4 based digitizer board. So this digitizer board accepts 8 analog single-ended input signals, 0 to 1 volt, and any high gain input pulse crossing the set threshold generates the trigger signal. So like this 8 analog signals and signal conditioning section is there, DRS for chip, ADC, and then one FPGA is there, where all this data will be digitized, and some temporary storage is provided so that we can record some events consecutively. And some event timestamp is also added to the data. And this is the photograph of this developed board. It is a 12 centimeter by 5 centimeter board, and some interface pins are provided so that we can connect these multiple boards on a single board. So this is a cluster digitizer module. 4 such DRS-based digitizer boards are plugged on to it. And this is the amplifier section where this low gain and high gain version of the input pulses is generated. And then this is the FPGA where this level 2 trigger generation. Level 1 trigger generation takes place in these mezzanine boards, and level 2 triggers are generated in this FPGA, and then they are routed to the CTM via this backplane connector. Here also we record this trigger hit pattern of 16 pixels. Trigger logic is there, and some scalars are there to monitor the rates of various signals. This is next module, that is data concentrator module. Its function is to receive event data packets from each of the 16 CDMs over 16 independent LVDS serial links, and then transfer the data to remote PC over 1 Gbps Ethernet links. So it is designed to have 2 identical sections. Each section will cater to 8 CDMs. It supports some local data buffering, so of 8 kilobyte per channel, and 2 high-speed Ethernet links are there, through which this event data is transferred to PC using TOE-based chips. So here we can see some block diagram of the firmware. This input serial data is deserialized and converted to 32-bit words, and then it is stored in the respective FIFO-based buffer, and then finally it is transmitted through this TOE module in a round-robin fashion by using token signal-based approach. And this is the last module, that is control and trigger module. As its name suggests, it has 2 sections, control and trigger. Control section uses soft-core processor. It powers on all the CDMs one by one in the beginning of the observations. So it manages overall control, configuration, and monitoring of backend modules. It has one RTC to less the trigger time with the 100 nanosecond resolution. So this is also implemented inside FPGA. It sends event number with timestamp to all the DDBs, and Ethernet link to remote PC using VisNet chip to receive all this configuration data and monitoring data. And trigger section, it generates the final trigger signal for the entire camera. It also generates the event validation signal to avoid the false triggers, and monitors rates of various signals. And it also caters essential service signals for all the modules like this final trigger signal and the basic clock. And all these modules, they are connected to each other via a custom designed SPI link. So all this shows the connectivity of all these modules. So here event marker information like from CTM, it is transferred, and various the CSPI link is there for transferring the configuration data from PC to control and trigger module, and then finally to all these DRS-based digitizer boards. This is the backend crate. We purchased one that empty this VME crate, and then designed a custom that backplane motherboard. So input supply, it takes plus minus 5 volts. So this is old photograph when we tested this mini camera, and this is with all the cluster digitizer modules.
So we can find PME without the packaging.
Yes, yes, and all those
Only the mechanical.
only mechanical structure was purchased.
All these,
Yes, the slots are there. So its depth is up to this, but our modules, they were not fitting into this depth. And then this was pushed little back. So this back side of this one. This is the data acquisition timing flow diagram. Suppose,
sorry,
yeah.
You're using a PME state, but there's nothing really resembling the PME.
Yes, only that mechanical structure we have used. Yes. So this is,
Would be, it is just a trade.
yeah, it is just a,
mechanical
yeah, mechanical housing. This is data acquisition timing flow diagram. So suppose for SiPM, they are seeing the light at same time. So then the level 1 trigger signals are generated in about 5 nanoseconds. Then level 2 trigger signals for this 16 cluster, this is generated in 50 nanosecond, and final trigger signal will be generated within that 50 nanoseconds. So after this, we have to receive this trigger hit pattern from all the cluster digitizer modules to the CTM. So that takes little more time, and then that information generates the event validation signal. So that happens within this 1 microsecond. So once it is decided that whether event is valid, then we start the digitization process. By then for this, at the beginning, we send the event timestamp information to all the digitizer modules. And once event timestamp information is sent, then actual digitization starts. So it takes about 32.7 microseconds at 120 nanosecond region of interest cells for 9 channels of a DDV board, and it takes about 398 microseconds to transfer this data to the data concentrator module.
So
Yeah.
from here,
Yeah.
how your signals are going to remain waiting for DRS to digitize. I mean, in this
Yes.
figure, the way it's shown,
Yes.
your digitization would start happening, yes.
In about after about the 7 microseconds. So
Your analog signals should be sitting somewhere, right?
yes, analog signals are sitting. So in next slide, I'll show about that when this thing. Yeah. Oh, sorry. It is okay. Okay, here itself I will explain. It is there in when I will describe about the DRS for chip. So once these analog signals, they are this sampling continuously goes on, then we send a stop sampling signal to the DRS. So which stops the further sampling of analog signals. So that happens about 700 nanosecond, and this is also configurable depending upon the where your analog pulses are arriving. So sampling is stopped at this point itself, and as per DRS4 specifications, we have to read all these stored signals within 1 millisecond. So that much window is there, and we decide within 1 microsecond whether that event is valid or not. If event is not valid, then here itself this digitization process is aborted, and again we make the DRS4 ready for fresh sampling of the data.
So 700 nanoseconds is the time when it stops.
Yes.
So where does it start? So it should, your one-fold is somewhere beside 5 nanoseconds.
Yes.
And your, yeah, the level 2 beside is at 50.
Okay, so maybe I'll show better on this. Oh, sorry. Yes. Oh, that slide is missing. That.
It's okay.
Okay. Yes.
If you want, you can use the board, but otherwise we can discuss it. Right?
Yeah. So this is a circular buffer. So it has 1024 cells. Suppose this is from 0 and 1023. So suppose our this analog signal, this has come here, and after 50 nanoseconds, this trigger signal is generated, and we are stopping sampling somewhere here, 700 nanosecond. So this is C stop. So, and then we are waiting for this. So this our signals, analog signal, they are frozen. So once this final signal for the digitization is received, so then we start sampling. So we can stop it anywhere. User can configure it. Suppose we want to stop it here, and then digitization will start from here. And like this we can.
So you have in this scheme about 650, because you said 1 gigahertz is what you're running, right?
Yes. Yes.
So basically you have about 650 samples.
Samples will be there.
Because maybe you have option to change.
Yes. Yes.
What is the total date time of the system then?
As it is shown, so this is about 40 microseconds at this region of interest.
So that
So DRS for chip has 1024 cells, so we can configure. So right now we have selected like this 120 nanosecond ROI. So 20 nanosecond is our roughly our pulse duration. So we want 50 samples before pulse and 50 samples after. So this can be further calibrated, and then this dead time can further reduce. And if you want to, for some in the beginning, like we are recording full ROI, so then this dead time will increase. But up to this much time, about 7 microseconds is always taken for any event.
so that 398 microsecond doesn't included in the dead time.
398
microsecond, that is not adding up to your dead time.
Which 19 microseconds?
398 microseconds.
Yeah, that is okay. So that will, this is just digitization time. This 390 microsecond for 1 dB, this dead time is there. So then we are using the same link to transfer all this data. So it will be shared. So roughly it will take about 1.5 millisecond to transfer data from 4 dBs of a CDM.
So 1.5 millisecond is your dead time.
Yes.
Okay.
So this is a camera software scheme. So this camera software is running, is divided into 2 parts. One, whatever, some firmware running in the camera modules, and another is in the PCs at the control room. So this is pixel cluster modules. Here microcontroller is used for control of the various components used on the bias supply board. So microcontroller firmware controls that under supervisory commands from the bias server. This bias server further receives commands from the main operator console, and then another firmware is running in this cluster digitizer modules. It takes instructions from the firmware running in the CTM, and then accordingly it responds. And this is the DCM, which transfers the data to the data concentrator PC, where this these data concentrators, they are running. It takes data from A and B, and then finally it is fed to event builder and stored in the file. So these are some of the snapshots of camera software GUI. So this is for database where we keeps the record of all the pixels and various other calibration coefficients. This is the main console GUI. Here, from here we control this camera operations and monitor some of the parameters. So like this is another snapshot. So where we are displaying this DDV packet efficiency, CDM packet efficiency, and various temperatures of different modules and trigger rates. So this is bias console GUI. So here we display these parameters related to the bias supply system of the camera. This is just a program developed for offline analysis of the data taken. This is one of the pulse digitized, and here like 1024 nanosecond region of interest is taken for this pulse, and it displays all this event information which we record in the camera. So now I'll present some of the preliminary test results. For storing, for analog sampling and temporary storage of analog signals, we are using DRS4 chip. This is the simplified schematic of one cell of a DRS4 chip. So analog signal is stored in the on a capacitor, and at the input there are two transistors, and outside one buffer is there. So this cell has some inherent offset due to this IC manufacturing process. So this is distribution of DRS4 cell offsets without correction for a cell for 1000 events. So this shows that this offset is quite stable, and it can be measured and corrected. So for this, we took the data without applying these input signals, and this is the pulse profile we obtained, and this is the distribution of offsets recorded. So after applying this calibration coefficient, so this is the pulse profile we obtained, and then distribution of offsets, which earlier distribution, it was about 8 millivolt that spread was there, and now it reduced to 0.5 millivolt. So this is after applying this parameters. So this is the pulse shape which we obtain. This is without applying offset correction. So here we can see this 2.5 millivolt pulse is not visible, and this is after corrections. Same version, high gain version, we can see. This is noise estimation for low gain and high gain channels was done. So about 0.6 millivolt, 0.63 millivolt was obtained when for this low gain channels, and of the same order for the high gain channels when these pixel amplifiers were disabled, and when it were enabled. So that time, so little increase was there in the high gain channels. So then absolute value of the low gain and high gain factors for 256 channels was also measured. So for low gain, we can see for 256, it is varying. This low gain factor is 0.7 with RMS value of this one. And this is the absolute value of the high gain factor. This is their ratio distribution for 256 channels. This is the linearity test performed. Here we varied the input pulse amplitude and recorded the output pulse amplitude. So this is the response for large signal linearity test covering the complete range. And this is the small signal linearity test where this high gain version of is shown here and low gain version also shown. So both are quite good linear. So this low gain and high gain, they can be used for intercalibration of the signals. So gain value here obtained is also about 15, and this is 0.8, which is matching with our previous measurements. This is time precision measurement was done. For this, we applied a pulse to one of the channel, and another channel, the pulse was delayed by using a cable of 1 meter length. So about 5 nanoseconds delay we will obtain. And then here we can see from this sigma value, so about 0.5 nanosecond that jitter we obtain for this high gain channels, and same thing for the low gain channels. This is the single photo electron spectrum. So it is used to know the number of photons detected at a pixel in an event. It can be used to compute that what is the silicon pulse amplitude for one photoelectron. And finally, it can be used for checking the linearity in a pixel response with increase in number of photoelectrons. So here in the distribution, we can see 7 photoelectron peaks, and this quite linear. So our high gain channel about 14 millivolt it gives for one photoelectron. This is just some plot of temperature variation, how it is varying across the 16 CDMs in the crate. And now this is about the mini camera that we tested at the one of the array, one of the telescope of tactic array. So here this central this cluster that was made ready, and we did some functionality and performance tests at Mount Abu by mounting at the telescope. So this is the telescope used, and here is the camera. We can see this is the backend electronics for this mini camera. It was done last year in May month. Then some.
Electronics is not at the focal plane.
This is at the focal plane. So here we can see this is the photon detection plane. So all these silicon photomultiplier and LC, they are at this, and just behind that this which is seen in this one. Here the front end as well as back end electronics is, yes. So this.
So that is the combined thing you said, half a kilowatt.
Yeah, that is for full camera. So this was 1/4 of the camera. Yeah. So one of the tests was that pixel rate versus trigger threshold, as I told earlier, that where to operate a particular pixel. So here we can see about 200 millivolt. And this is one of the Cherenkov event captured by this mini camera.
So 200 by 14 millivolts.
Yes.
What give you the number of photons?
Yes. So when we tested this camera at Mount Abu, so this telescope was not having all the mirrors, and whatever mirrors were there, they were also not of very good quality. They were gone for, yes, recoating. So that's why this is seen little higher side. So this is current status. So after testing of all front end and back end electronics individually, they were coupled together, and all these sensors, they were also characterized, and then integration tests are going on for the camera. This is few photographs during assembly process. So that side front end electronic, this is back end electronics crate, and then finally it is housed that it is fully covered. So this is front side. So now lab tests are going on. So camera is placed inside this large black box of about 4-meter length. So summary, this modular hardware for ease of control and maintenance, this was adopted for the camera, and all the hardware is quite user configurable. Like we can, user can set the region of interest cell and what trigger threshold you want to operate, and trigger scheme also one can select whether 3 NCNN or 4 NCNN based, and user can enable or disable individual channels of the camera. Pulse profile recording at this rate, event acquisition time about this much, and sustained trigger rate about 500 Hertz at 120 nanosecond ROI. And this is the event data size for 1 hour observation at this ROI and 10 Hertz event rate about 4.8 GB. Power consumption per pixel is 1.9 watt. This is for front end as well as back end electronics combined. And cost estimate about 25,000 for the DAQ, and roughly about same cost for the 1 pixel sensor. And camera weight is about 900 kg.
90.
Oh, sorry, 90 kg. These are some of the papers which were published from this work, and some conference or symposium proceedings. So this camera development team, so some members from our group, from other groups, some of our members were retired, and the students. Thanks.
Thank you, Sandeep. very, very nice colloquium. In fact, some of the members, first Acharya is here, and quite a few of the colleagues, Suresh Upadhyaya, Navan, somebody disappeared. Kiran Gote, they're all here, they're team members. I think before I take questions, I think there are a couple of points that were asked. So I will like to get them clarified. One question was about, I think, longitudinal and transverse structure of your gamma or cosmic. Varsha or Acharya, if you can little bit more elaborate on it, the figure that he has shown in the, I think, one of the
footprint of
first
showers.
slides. There's a mic is there right behind.
Okay, if it is like if shower is landing at the place of the telescope itself, you will get circular as you are claiming.
Here.
And if it is at some distance, like shower is landing somewhere here, your telescope here. In that case, light is like, let us say like there is some circle and light is coming like this. So it will be elliptical. Yeah.
Okay, thanks. And also, Upadhyaya was actually sending some comments. Unfortunately, I didn't receive on my machine, but they are, I think, coming here. Suresh, do you want to unmute and clarify, I think, something about the dead time and some other comment I think you made. Oh. Upadhyaya, can you hear us? Hey, can you open the chat box? Suresh has opened. Yeah, Suresh.
Not able.
No, now we are able to hear you. Please go ahead.
Okay. So what I was trying to say is because people felt 700 nanosecond, why so much delay and all this thing. I think most probably he has explained. This is basically depends on the pulse, initial event when it happened. Accordingly, with respect to event, whether you want to record what pre and what post, depending on that, we will be adjusting this 700 nanosecond out of 1000 nanosecond. That is the first comment what I said. And second is dead time, 398 microsecond is the worst case. There are a lot of data memories in the TDB and CDM, and also CTM, so which will capable of storing several events. So definitely dead time will not be that much. It's only worst case scenario if the trigger rate is very high.
Okay. Thanks, Suresh. I think that was good that you clarified both the points. Okay, please be online.
Yeah, sure.
Okay. I think those are the points I thought I'll get them corrected before. Okay. So now, any questions from audience, both online as well as in person? Yeah. Please hold on. Please talk. Please.
Electronics.
No, you have to.
Hello.
Yes.
Whatever you are in the box, who make box? Ready-made available?
Who made
Boxes. Casing.
Yes.
You design or outside made?
No, it was designed by our that DHEP workshop members.
I think
Okay,
he's Chauhan, right? Santosh,
Yes,
no?
Santosh.
Okay.
And it's fabricated outside in the country. I mean, customized.
Okay. Achha, what is the total size? Camera size?
That is about this 70 by 72 centimeter and about 3 feet that length.
Okay.
This much. So from this to this about 90 and this one 70 by 72 centimeter.
Any other questions? Where? Please use mics.
Okay. So how you implement that soft core IP in your design?
Soft core IP.
Soft core
Processor.
Yeah, soft core processor. This NEOS. This is proprietary of that Altera.
Okay.
So that for that they have given this software Eclipse. So we run through that, and then hardware and the soft code, they are combined together, and then final firmware file is generated, and that we store into the flash memory of the FPGA.
Okay, thank you.
In one of the figures in the very front end, you have a microcontroller firmware you have written. That's not the software, right? That is.
Yeah, microcontroller firmware is also software.
Is a standard microcontroller?
This is from Atmel microcontroller, X Mega series microcontroller is there. So that
okay, not the software.
No, that is a physical.
Okay.
No, it's a firmware.
I think there are no more questions. So.
I had a question, Satya.
Yes, sir.
Can you hear me?
Yeah. Please
Yeah. Okay. My question is the following: Is this sort of camera ultimately going to replace the photomultiplier camera in MACE telescope?
So right now we are developing this one, and it is designed for 4-meter class telescope. And whether about this plans for MACE type of telescope or other one, so that maybe Varsha can comment whether people have plans.
What I hear from BRC colleagues is that they have planned for 2 more telescopes of MACE size, and they want to have SiPM based camera for both those telescopes. So now we'll have to make lots of changes in this design. Probably we'll have to go for ASIC based design, etc. Because pixel size is much larger. So electronics will be too much, like if we go with same approach. So probably we'll have to go for some compressed things with ASICs.
Okay, since you are there, maybe I can ask. Can I ask another question? Namely, the use of a silicon PM, will it help in getting more detailed information about a shower as compared to, let's say, the photomultiplier, which will be, of course, which must be more coarse as compared to sampling done by the silicon pixel camera?
Okay, it will increase observation duty cycle, because it is possible to then operate telescope partially during moonlit part of the night. So some of the transients otherwise you miss because you are not able to operate. Other thing is that photon detection efficiency is higher compared to PMTs. So that will also help. Slightly, one can go for lower energy threshold.
Okay. Thank you.
Okay, sir. Okay, so with that, there is thank once again, Sandeep, for really an excellent work and excellent colloquium. He and his team, as we always express our thanks to the colloquium speaker by awarding this gift. I think Mandar wants to take a picture. Is it okay? I'm here. Yes. Okay. Thank you. Thank you. Thank you very much. And please join for a cup of tea in the West Canteen.
Shall I join?
Please come. Please come. You all have to come physically. Then you get. There is no city.
Within next 10 minutes.
Yeah. E-copy.
I will send a voucher.
Oh, no Swiggy.
Asset has to send the voucher.
No Swiggy business.
So income is a lot of noise.
Yes. Okay. You, Mike, you can take over.
Yeah.
Here.
Thanks so much.